Welcome to Ms. Taylor's class notes, and today we're going to be talking about rotations. So the first thing that I want us to make sure that we understand is the difference between clockwise and counterclockwise. So clockwise, we're going to go to the right just like a clock would, whereas if we are counterclockwise, we go to the left opposite of the way that a normal clock would go. So when we do rotations, we talk about clockwise and counterclockwise, and it's important for us to understand the difference between clockwise, you go to the right, counterclockwise, you go to the left. Most of our rotations we're going to do are going to be counterclockwise because of the way that we label the graph. So when we label the graph, I like to use our C metaphor because, again, clockwise and counterclockwise. So our quadrants are 1, 2, 3, and 4. And because of this, 90% of the time, we are going to go counterclockwise when we are doing our rotations. If it doesn't say what direction to go, assume that it means counterclockwise, but occasionally you will see a problem that says rotate clockwise. And so again, this is just a real quick note. Assume everything is counterclockwise, and all of our rules are written for counterclockwise. However, if they ask us about clockwise, our 90-degree rule for counterclockwise is the same thing as 270 clockwise. 180 is always going to be the same. And then if it's 270 counter, that's the same thing as 90 degrees clockwise. Oh, I can't spell today. That's not anything new though. All right, so now let's kind of talk about our definition of our rotations. So rotations are where we transform a figure around a fixed point, and that fixed point is the center of rotation. For us, the center of rotation is always going to be the origin. And again, rotations are rigid motions, which means that all of our shapes should be congruent. This is going to come in handy later when we start talking about congruent versus similar figures, but right now everything we've done is a rigid motion, and so they are congruent. All right, so this first problem wants us to rotate 270 degrees. So our rule for 270 degrees is x comma y comma negative x. And so we're going to take our points. So we have r, which is 3 comma 1, s, which is 5 comma 1, and t, which is 5 negative 3. And we're going to apply our transformation. So we're going to switch the x and the y. So the 1's going to go first, and then we're going to make our x negative. Switch our x and our y, make the x negative. Switch our x and the y, and make the x negative. So that's r prime, s prime, and t prime. So if we graph the original, 3, 1, 5, 1, 5, 1, 2, negative 3. Oh, there's a u. I forgot about u. Let me real quick write down u. 2, negative 1. And then it becomes negative 1, negative 2 would be u prime. So we've got t, s, nope, that's an r. R, S, T, and then U. And so if we graph our image, because R, S, T, U is our pre-image, so our image is going to be 1, negative 3, 1, negative 5, negative 3, 1, 2, 3, 4, 5, and then negative 1, negative 2. So R prime, S prime, T prime, U prime. And yep, it looks like the same shape. And yes, it has been rotated 1, 2, 3 quadrants, which would be our 270 or 90. So that would be 90 clockwise. That would be 270 counterclockwise. So our 90-degree rule is x comma y negative b comma a. Negative y comma x. So if we've got triangle JKL, J is 3 comma 0, K is 4 comma 3, and then L is 6, comma 0. So when we make those transformations, we're going to flip the x and the y and make the y negative. 0 is unable to be negative, and so we just leave it as 0. So we're going to make the negative 3, or the 3 negative, and then again, 0 cannot be negative. So we graph our original. So we've got J, K, and L. And we're going to rotate it 90 degrees clockwise, which is 1, 2, 3, 6. So J prime, K prime, L prime. And again, that is 90 degrees clockwise or counterclockwise or 270 degrees counter. No, 270 clockwise is 90 degrees count. Sorry, guys. All right, I want you to do this one on your own, and I want you to check with your completed class notes. All right, so here we've got compositions with rotations. And so a quick reminder that compositions means 2 or more. And so this is where our handy-dandy transformation reference sheet on the back of our notes is going to help us out a lot. So a reflection in the y-axis is going to be the rule x negative y. A rotation 90 degrees is going to be negative y, comma, x. So if we take r, just r, which is 1, comma, negative 3, and s, which is 2, negative 6. If we perform our first transformation, which is just to make the y negative, r prime is going to be 1, 3, because the negative and negative makes it positive. So then s prime is going to be 2, 6, because again, our reflection in the y-axis. Oh no, that was the x-axis. Sorry guys, I wrote the wrong rule. I'm going really fast today. It should be negative x. I thought something went wrong. So all of these are going to be different. And that's the hardest part about this, is just making sure you have the right rule and doing the right thing. So it should be negative 1, 3, and it should be negative 1, negative 3, and negative 2, negative 6. And so then we've got r double prime and s double prime. And remember, when we do these compositions, that we always use our most recent transformation when we use our new rule. So we need to flip them and make the y negative. So the 3 becomes positive. The 6 becomes positive, and so those are going to be what we graph. So r is going to be 1, negative 3, and then 2, negative 6, so that's r, and then that's s. Then we reflect it across our y-axis, which gives us negative 1, negative 3 for r prime, negative 2, negative 6 for s prime. Oh, let me connect these to make a lot more sense. And then we've got our rotation, which is 3, negative 1, and then 6, negative 2 for r double prime and s double prime. And again, that is 90 counterclockwise, which is the same thing as 270 clockwise. All right, I want you to do this one on your own and check with the completed class notes. All right, so today we're going to talk about rotational symmetry. So rotational means that we can rotate the figure, and as we rotate the figure, it's in the exact same place. The only way that they have rotational symmetry is if we rotate them 180 degrees or less, about the same point, and the figures are the same. So this first figure here, our parallelogram, yes, it has rotational symmetry. If we rotate it 180 degrees, it is going to be the same shape. Our trapezoid does not have rotational symmetry because this line is not the same as that one. So when we flip it 180 degrees, it will not be the same. So our rotational symmetry and our line symmetry have a lot of things in common. So if a figure has line symmetry, we know that it also has rotational symmetry. So we can use our line symmetry to figure out how many degrees we can rotate it before the shape is the same. So if we look at our equilateral triangle, we know that it has 3 lines of symmetry because all the sides are the same distance. And because they're all the same distance, since it has 3 points, we know that it has 3 lines of symmetry. So what we do is we take it's kind of sort of a formula. 360 is the full degrees of a rotation. And because it has 3 lines of symmetry, we know it's going to rotate 3 times and be the same. So we're going to take 360 and we're going to divide it by 3. So we get 1, we get 2. So this shape, our equilateral triangle, has 120 degrees of rotation. So every 120 degrees, when we rotate it, it's going to be the exact same shape. All right, so now we've got another parallelogram. We know that we can cut it in half there and it's the same. And we know we can cut it in half there and it's the same. So if it has 2 lines of symmetry, we can take 360, divide it by 2, which gives us 180 degrees of rotation. So our star figure here, we've got a line of symmetry there. We have a line of symmetry here. We've got one there, and then we've got another right here. So because we've got those 4 lines of symmetry, we can do 360 divided by 4, and it's going to have 90 degrees of rotation. So if we look at our right triangle here, this line is not the same as that line, is not the same distance as that line, so this does not have any rotational symmetry. It also does not have any line symmetry. So if we look at our sun is going to have a lot of points of rotation. So we're able to cut it in half there, 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 and then we're able to come back and cut it in half there, 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 and then there. So that gives us 1, 2, 3, 4, 5, 6, 7, 8 lines of rotation. So we're going to take 360 and divide it by 8. So 8 will go into 36 4 times, which gives me a remainder of 40, which is 5. So it has 45 degrees of rotation.